Alright, boys and girls, welcome back to the drive-through. Here with some pre-calc help, okay? This is a question that's going to give you problems, and I want to help you understand what the projection of V onto W is telling you. So first, like always, let's draw a good picture. So we got 7, 3, 1, 2, 3, 4, 5, 6, 7. Alright, so here is V. Let me change that to a solid. Sorry. Okay. Now here is W. Left one, up one. Alright, now, the projection of V onto W is asking you this. How much of the green vector is heading parallel to the blue vector? Whoops. So, if I create a little line tool here, we're asking how much of the green vector is going in that direction. Now, the easiest way for me to conceptualize this is like, imagine that you had a flashlight and you were shining it down. Oh gosh, what a terrible flashlight. Now it's a decorative flashlight. Alright, that's better. If you were shining this flashlight on top of this scenario, the shadow, if it was perpendicular to the blue line, this shadow here would create, this right here would be the projection of the green vector onto the blue vector. Okay? It's the amount of the green vector that's traveling parallel to the blue vector. In physics, this becomes incredibly important. Now, there is an equation for this. So the projection, let's see, of V onto W is V dot W over the magnitude of W squared, that just makes sure it's positive, times the W vector again. So this dot product is kind of giving you the compatibility, how much is in each direction, and then you put it over the magnitude of W squared to what's called normalize it, and then you multiply it back by the vector. It's wild. But let's see what it gives us. Okay? V dot W. So that would be 7, 3 dot -1, 1. The magnitude of W would be the square root of 1 squared plus 1 squared. So that's radical 2 squared. And we're going to take that and we're going to multiply it by -1, 1. Okay? So this is just going to be a number on the left side. 7 times -1 is -7. 3 times 1 is 3, and we do all of that over 2 times this vector. So what do you get over here? You get 4 divided by 2 is 2, and 2 times this vector is -2. So, oh my gosh, look at that. That's exactly what we understood visually. So what this wild formula is telling you is how much of the green vector is traveling in the blue direction. Now that you may not care about that at all, but let's say, like, I don't know, you're dragging a sled. So you got a sled, and that sled has a bunch of weights on it. A bunch of weights. Well, I think you understand that if you pulled this in that direction, and it's important to understand, this is the floor here, okay? if you were pulling those weights in the direction of the blue vector, I hope you don't expect that the weights are going to move very much, because the majority of your motion or your strength is being pulled perpendicular to the floor. But if you applied the pressure in this direction, I hope you understand that it would pull it much more efficiently. You want to pull parallel to the motion. So this is kind of the effect that this math is having, and that's why it's important we learn it now, because you're going to use it in physics. I hope that helps. Marissa, thanks for the great question. Boom!